this is Jason Kendall, and welcome to the next of my introductory astronomy lectures. We're rounding out the nature of measurement of the stars and stellar measurements in general, and we're going to link a whole bunch of things together in order to get distances. So distances were first introduced to us with parallax, and the Hipparcos mission, which ran in the early 1990s, generated an enormous list of parallaxes to nearby stars. Roughly about 1 million with really good precision, and about 2.5 million with poor precision. In any event, the highest precision measurements are approximately 100,000 or so stars from this particular mission, and parallax was incredibly important just to do this measurement. So the Hipparcos satellite changed astrophysics when it did it. However, the Gaia mission, which was launched in 2014 and then did its first data release in September 2016, changed even more things. And its data, will actually get parallaxes for over 200 million stars and get proper motions and positions for 1 billion stars. So its maximum precision was about 10 microarcseconds, or about 1% of a milliarcsecond. And so that means it can get distances out to 10,000 parsecs, or approximately a quarter of the way around the galaxy, which is really amazing. And definitely almost to the center of the galaxy, if you could see through things. So I put the website link for the Gaia mission there, because it's one of the most important missions. And it doesn't make pictures. It doesn't make pretty pictures like the Hubble Space Telescope, but yet its impact will be greater. The trick is that we're actually going to find that we can use the distances to stars, or actually derive the distances to stars, by simply looking at the brightness of two stars in two different standardized filters. And we'll call those filters the Johnson B and Johnson V, because they tend to be the most widely used. But of course, things are used in different filter techniques. You could do that too. Notice we have, from the Hipparcos satellite, we have an HR diagram, about 22,000 stars. And there is a link between the color of a star for a main sequence type star and luminosity. And you can see that the trick is that, well, what about those giants and the white dwarfs? They kind of mess things up. But if you can somehow assure that you've got a main sequence, then you can actually determine the distance of things, because you can calibrate, because all stars fall on this main sequence. Doesn't matter where they are. If they're a main sequence star, they fall on the main sequence. So if you can get a group of stars that happen to be at the same distance, then they may have a distinct main sequence. And if you can use that, then you can get to find this group of stars. And that is called spectroscopic parallax. Spectroscopic parallax doesn't really have a lot to do with geometric parallax, but it does actually. It actually uses spectroscopy to find the distance. So what we're going to do is we're going to measure the apparent magnitude or apparent brightness of a star and its spectral class or its color. Spectral class is much more important, actually, but that involves a good spectrum. But color, with just a difference in brightness of two filters, which is much easier and more common. And you can find the luminosity class, but then to get the luminosity class, you definitely do need the spectrum, unless it's in a cluster. And then you can apply the inverse square law to find the exact distance. Or you can use the distance modulus equation, which we'll look at later. Spectroscopic parallax in greater detail is a distance-independent property. So that is the parallax itself, but the observed spectrum. So if you can get a high-resolution spectrum, that tells you the star's temperature. The star's temperature gives you the luminosity, as we've seen from the luminosity radius temperature diagram. So if you have a good knowledge about the nature of the luminosity class, which means that it'll tell you where it is on the HR diagram, and that unique location on a calibrated HR diagram gives you the distance. How you do that? Well, first you make an enormous HR diagram of as many nearby stars as you can, and you make sure you get a good parallax for all those stars. And the most important group of stars in the sky is the Hyades star cluster. That is the most important one. And because it's the closest star cluster, and it's a relatively young star cluster. So it's the most important thing, and we'll see why shortly. And then what you do is you get the spectral type and luminosity class of some star from its spectrum. Remember, though, that the widths of lines depend on the luminosity class. And then you locate the star in the calibrated HR diagram and just simply read off the luminosity, and you compute the distance from the measured brightness of the star. So you know what the luminosity is because of the calibrated HR diagram. And then from that, you can get the distance given that you can measure its apparent brightness. So how does this look? Here we have kind of a sketch of an HR diagram, and we see a bunch of stars on a main sequence. And there is a first one that says, well, what type of star it is. It is an A8V, which means it's type A, spectral type A, subclass 8, and luminosity class V, or dwarf. And if we have a calibrated HR diagram, meaning we know exactly what the luminosity of all A8V type stars are, then all we have to do is make sure that we have one of that, and that gives us the luminosity of it. It may be 10 times the luminosity of the sun. Maybe it's that. And then if you find that it's very, very dim, then it must be very, very far. And so you calculate exactly how bright it would be compared to the sun at such and such distance, given that it is 10 solar luminosities, or 10 times the luminosity of the sun. How far away would something have to be in order for something 10 times the luminosity of the sun in order to have the brightness that you observe it to be? Also, the same thing is that you might get distracted and say, oh, it's also it's a spectral class A, subclass 8, but it is a bright giant, which would mean a luminosity class 1. And so that would be, as a bright giant, 22,000 times the luminosity of the sun. So now we have two stars with the same spectral class, but different luminosity classes, which lead to incredibly different luminosities and therefore different distances if you measure them to be the same brightness. An A8V star with the same brightness in the sky as an A81 star, then the A8V star must be much closer than the A81. So if they were at the same distance, then the main sequence type star, the V luminosity class, would be very faint compared to the other. So our best thing, though, is we need to calibrate the HR diagram. So let's see what we can do. And again, let's just look at the various luminosity classes as I jump the gun there a little bit, because I always forget what the order of my slides are, and it's just how that goes. Luminosity classes, there's roughly about 1, 2, 3, 4, 5, 6 sort of luminosity classes. There's two different groups of supergiants. One group of bright giants, then there's subgiants, and dwarfs. Everybody's a dwarf that goes on the main sequence, even though that some of them are pretty large. It's just how they're classified. White dwarfs are not given in this diagram. But again, remember that the larger the star, or more specifically, the closer to luminosity class 1 they are, the narrower the lines. And the absorption lines for main sequence stars are the broadest because they're the densest stars. And density means higher pressure. Higher pressure means the atoms are moving faster in the atmosphere of the star, and if they're moving faster, then they can absorb and emit wavelengths of light that are off of the normal wavelengths of the atomic transition of that particular atom. But when they're giant stars, the atoms and molecules are under low pressure, which means their relative speeds are lower with respect to each other. So you get less and less Doppler broadening of the lines because the atoms and molecules are moving slower, so they can really only absorb at the wavelengths that are corresponding to the atomic transitions. So that's why the luminosity classes are different. Here's some difficulties with doing this thing, and it's really hard to use it for individual stars, and it works best for star clusters. We're going to talk about that in just a little bit. And despite the name, it only uses geometric parallaxes to initially calibrate the HR diagram, make a massive calibration. So global studies such as Hipparcos and Gaia are critical because that helps you to calibrate the distance. So you use massive numbers of geometric parallaxes to calibrate the HR diagram. And once you've done that calibration in the geometric parallaxes, you don't no longer use geometric parallax because the goal is use the spectrum, not the parallax. Maybe you can't get the parallax for this particular star, but you can get its spectrum because the spectrum is in the light, and that's what you're observing. You don't directly observe parallax unless you wait for the Earth to move around the sun. And so that typically is not how long it takes to do a spectrum. In any event, the practical distance is about to 100,000 parsecs, but really that's best for star clusters. And this is now well extended due to the Gaia mission. The luminosity classes are really roughly defined, so that makes it trickier because Yeah, you're talking about widths of lines. So as you can see from the HR diagrams that we've shown, that once you put a huge number of stars out there, the luminosity classes start to blend together. So you really do have to, it's a bit of a trick. So there's a bit of hand wavy magic with number 4 there. And if you have faint spectra, well, it's really hard to tell the main sequence star from a giant. It actually gets very difficult if the spectra are very, very faint. And we haven't really talked about this too much, but the HR diagram location also depends gently on the composition of the stars. So that will come into much later when we think about the nature of how much hydrogen and helium and other elements are in the atmospheres of the stars. And so if there's slightly different composition to the stars, meaning or significantly different, more it's always hydrogen and helium are the dominant things, but what the other stuff is, what the proportion of the rest of things like carbon, nitrogen, and oxygen, iron are in the atmospheres, that will affect the location of the star in the HR diagram. But for an introductory purpose, like an intro astronomy thing, number 6 is not really our main thing. The main thing for the difficulties with spectroscopic parallax and introductory level, because it's, spectroscopic parallax is not parallax. And luminosity classes are hard to do, and faint spectra are really tough to use. So getting good spectra is critical. Well, how can we get around getting good spectra? And it's called poor man's spectroscopy, is again using standard filters. And again, here are standard filters from, say, from Bader. And these standard filters are the Johnson UV, VR, and I, with B and V being the most common. And we can see them installed on the back of a telescope here. So a telescope would simply take a picture through that filter, and the camera itself would not be a color image. It would take a black and white image, meaning recording all the photons that it receives and not photons of a given wavelength in a given region. See, a color camera looks at, it does this filtering process for you, meaning if it lands on this pixel and that pixel is sensitive to green, then you'll get a green pixel, or light there. And if lands on the pixel that's sensitive to red, you'll get a little bit of a hotspot of red on that image. But most astronomical imagery says, give me a really even response across all wavelengths, and I'll put a filter in front of it, and then I'll only be looking at the red or the yellow or the green or the blue light, and then I'll reconstruct the color image post facto from this image. That's usually how it's done. So given that that's how it's done, the B and V filters tend to be the ones that are used more frequently, and in fact the V is dominant for variable star observations. So the difference in brightness, again, can be measured in 2 filters, and that determines also the temperature of the star. So if we standardize things and use the most common, which are the B and V filter, we find that the B and V filter is really the difference in brightness between, say, the blue line and the yellow line that we see here across these spectra. We can see that they definitely show the color and therefore temperature of the star. So let's take our most important star cluster in the entire sky. This is the Hyades. And it's kind of hard to see the Hyades in this image, but it's an overdensity of stars that lies at the center of this image. So this image includes, if we look carefully, the center of the Taurus the Bull, and the V of Taurus the Bull is inside of this group, and that is the Hyades. So if you look at the head of Taurus the Bull, that is the Hyades star cluster. It's approximately 153 light years away, or 47 parsecs. And the real trick for getting the distance of the Hyades is determining which of the stars in this field is actually part of the Hyades. So extended studies for parallaxes and proper motions need to be done for the Hyades in order to determine who is a member of the Hyades. And also spectroscopic studies are important too, because that tells you about composition as well. So the Hyades star cluster is in the center of this diagram. You could kind of see that it fades away off to the left, and you can see, oh, there's an overdensity here and an underdensity there. And that's what we mean by a star cluster. If we then calibrate and look at the Hipparcos data and the TICO data and some other data from another group, and we combine them together and filter out all the stars that have roughly the same distance, roughly the same parallax, and roughly the same proper motion, then we get what's known as an HR diagram for the Hyades. And what we're measuring here is the Johnson B filter minus the brightness in the B minus the brightness in the V. So that's the color across the bottom, and that's what this graph is reading. And the left-hand side is the apparent magnitude of the stars, not the absolute magnitude, but the apparent magnitude of the stars that we're looking at in the V filter. So this is called a color magnitude diagram, where color is on the bottom and magnitude is on the left. And remember, magnitudes, a difference in 5 magnitudes is 100 times brightness. So there are some stars in the Hyades that are magnitude 5, and there's some that are magnitude 4, and even a couple that are magnitude 3. And so magnitude 4 and 3 stars are visible to the naked eye. In fact, most of the ones in the upper left-hand corner of this thing are naked eye stars. So when we look at the Hyades in the sky, we see maybe 15 or 20 stars, and they seem to be grouped in the sky. And that's the upper left-hand corner that we're seeing. So those are the brightest and the bluest of the stars. And we see a distinct main sequence going all the way down to magnitude 16 or 17 with the deepest red stars, red dwarf type stars, and some white dwarfs also in the lower left, and a couple of giants in the upper right. So when we look at the Hyades, we got a few red giants, a bunch of blue hot stars, and that's what we see with our eyes in the sky. But what deep study actually shows us that there's a lot more there. So what we can do then is now we have a main sequence. And since we have a main sequence and we have a distance to the star cluster, we can use that. And therefore, remember, brighter goes up to the left and hotter goes left. Gets hotter to the left as well. All right, how can we use that? And now we can use this idea of a calibrated cluster from first getting the distance to the Hyades. We can now use that to go get the distance to the Pleiades. How can we do that? Well, all right, so we now know that stars are roughly the same thing, and we know that the Pleiades has a main sequence too, and I'll show you that in just a second. We will find that it also has a main sequence, and the more stars that we can get that are members, we get a tighter main sequence. We can eliminate the ones that we know are not part of the cluster, or even just ones that seem to be outliers and we're not really sure about them, so we just ditch them. That's frequently what happens. If you get some bad data, you just kind of dump it. And there's nothing wrong with that. If you're not sure about your data, why would you keep it? All right, so the equations that we're going to use are on the top one. The top one shows the brightness of, say, one star, B sub 1, compared to the brightness of another star, B sub 2. So we say, how much brighter is B1 compared to B2? And that's strictly dependent on their distances, given that they're the exact same kind of star. So two stars that are exactly the same, but are at different distances, number 1 and number 2, distance 1 and distance 2 for the same brightness of same type of star. How bright they are is dependent on their distances. So the inverse square means that if one star is 10 times brighter than the other, then it must be the square root of 10 times, or well, let's make it easier on ourselves. Let's say the brightness of 1 is 100 times the brightness of 2, and they're exactly the same type of star. Then therefore, number 2 must be 10 times further than number 1. That's what that top equation says. But our more important thing is that we can actually shift that into brightnesses again and look at two different or the same kind of star again. And instead of turning in terms of brightness, meaning how many photons per second, we can use astronomical magnitude. And that's what M1 and M2 are in the middle equation. So if you take the apparent magnitude, and the lowercase m for magnitude is always magnitude. Sorry, not mass, magnitude. Magnitude shows, yeah, I know, you're going to see this a lot, which is it, mass or magnitude? But when we talk about brightnesses and star measurements, we're going to be talking about magnitude. So sorry about that, but off we go. One of the wonderful things about astronomy is that you get to use the same thing for magnitude as mass. Whoops, off we go. So imagine again, it's the same kind of star, and they have different apparent magnitudes, m sub 1 and m sub 2. The distance modulus equation, we're getting really close to that, or the difference in brightness, and we define magnitudes are, now we take the distance between them, distance 1 compared to distance 2, it then is the log base 10, or the base 10 logarithm of the ratio of those two distances, yuck, times 5 is equal to the magnitude difference between the stars. And in fact, that is the definition of magnitude right there. And the distance here now is in parsecs. That's how we're going to be actually defining things, in terms of parsecs. So now we didn't say what the distance measurement is. In all of these cases, all three equations, the distance is in parsecs. So now let's play an interesting and important game. we've always been using the same kind of star. We said, well, it's at some distance or whatnot. We take the star, and what if it's 10 times further? What if it's 100 times further? What if it's 10 times closer? Blah, blah, blah. But now we're going to fix it at a particular distance. Let's pretend that we can move the star, and that we'll make a reference point. What is the magnitude of the star, m sub 1, if d sub 1, the distance, is 10 parsecs? So if the distance to a star is exactly 10 parsecs, how bright would it be if it's closer than 10 parsecs or further than 10 parsecs? And that's where the capital M comes in. Again, not mass, that's absolute magnitude. So the absolute magnitude of a star at 10 parsecs is actually a reference of luminosity. Because if we pretend that all the stars are 10 parsecs away, then if they have a brightness difference, then that's an intrinsic brightness difference. So the last equation is called the distance modulus equation, and that tells you that, so now the distance to the object is in parsecs. Lowercase m is the magnitude or brightness that you measure in magnitudes. And capital M is absolute magnitude of it. So you somehow have to have a handle on the absolute magnitudes in order to get the distance. So that's what we're going to really play with. So what people have recently been doing with the Gaia study is actually really trying to finely calibrate this HR diagram just specifically for the Hyades. And this comes from April of 2018, and this is Stellareno and team. This is April 28th for the monthly notices of the Royal Astronomical Society, MNRAS. And I give the link here for you to go peruse. But this is a much, from the previous ones from Hipparcos data, this is from the Gaia data. And how we read this graph then is a little different than the previous graphs that we showed. Again, we have the Johnson B and Johnson V filter color, meaning the brightness in those two things. But now they've taken, as a result of knowing the parallax due to Gaia very well, we can now use the absolute visual, absolute magnitude in the Johnson V filter. That's what capital M sub V here stands for. The other two, the B minus V, are simply the magnitudes of the B and V filters. The left hand, the y-axis going up and down, is the absolute magnitude. And now we know the absolute magnitude because we know the distance to the star cluster because we have parallax, thanks to Gaia, which gave an incredibly good parallax. And the tricky thing is, notice that the error bars, which are the horizontal lines going left and right, show how well we know particular data. For bright stars, it's fairly easy. But for dim stars, it gets trickier because the B and V magnitudes are not well determined for dim stars. These are close stars, too. They're only 150 parsecs away, only 150 light years away, or 40, 50 parsecs. And even now, the magnitude difference for looking at an M dwarf type star, that you can see that it's really hard to measure their brightnesses because in standard filters, they're actually really dim stars, so they're hard to measure. And this was an incredibly important thing to do, is actually try to get this distance measurement. And that black line that kind of traces through it, we'll get to what that is, but that basically describes what that's an interesting thing that we'll talk about, but it relates to the age of the star cluster, and we'll talk about that later in future lectures. So here are the Pleiades, M45, and it has Messier object 45, sometimes called the Seven Sisters. It's about 400 light years away. The distance across this cluster is about 13 light years. The blue reflection nebula people think that it's actually, the star cluster is actually passing through this nebula and illuminating it, or at least illuminating it from behind. The star cluster is mostly in front of it, so it's a reflection nebula material as the star cluster passes through it. So it's actually not thought to be part of the cluster. What's neat is that the Pleiades is in roughly the same direction in the sky as the Hyades. So if you pulled out from this picture and looked to, say, your to the east of the Pleiades, you would see Aldebaran and the Taurus the Bull, and you'd see the Hyades as a V-type shape in the sky. So the Pleiades are are a nice little group, and sometimes people think that's a Little Dipper. It's not. That's not the Little Dipper. It's the Seven Sisters, and you get to see them in the sky. There are about 3,000 stars in the Pleiades, or Messier 45. And that lets us to say, well, if we got a cluster of stars, maybe they're roughly at the same distance. Yeah, let's see what we can use that for. There's another group of stars, another double cluster, the Perseus double cluster, about 7,000 light years away, which has been known for a long time. And if you get extraordinarily dark skies, you can see this with naked eye. It can actually be seen as just two little fuzzy clouds close in the sky. And through a telescope, it looks very, very pretty. So it doesn't look like this. This is a long exposure, but you get to see the two groups of stars in the sky. And they're roughly at the same distance. And they're only separated by a couple hundred light years, but at 7,000 light years away, they look close together in the sky. So now what we can do is we can take the color, the B minus V color, and plot it compared to the apparent magnitude, the apparent visual magnitude for both the Hyades and the Pleiades. And HRD here stands for HR diagram. And the blue dots are for Hyades and the red dots are for the Pleiades. Now, stars are the same everywhere, and that's what we learn. And if we know the distances to the stars, we can calibrate the HR diagram. So the only reason that the Pleiades HR diagram is below and therefore fainter than the Hyades HR diagram is because all of the stars are farther away. So all we have to do is then say, how far up must we raise the Pleiades in order for it to match the Hyades? So they're the same things. They're all stars, and they're all A-type stars or B-type stars or M-type stars or F-type stars. The only reason that they're dimmer, meaning farther directly below, is that they're farther away. So that allows us to then say, if we calibrate the distance to the Hyades and we want to know the distance to the Pleiades, all we have to do is measure their apparent brightness, V, measure their colors, B minus V, and then see what the difference is between the Hyades and Pleiades. And then we get the distance to the Pleiades. And that's how we know that the Pleiades are about 400 light years away, is because of that. So let's scroll back a bit. And that's right, about 400 light years away by looking at the HR diagram of the Pleiades. And that's where we get this thing from, is at that distance. So measuring the distance to the Hyades gets you to all these different star clusters, and star cluster after star cluster. In fact, another set of Gaia data, if you go Googling around, shows another group using the Gaia team to make like tens of HR diagrams of nearby star clusters, and putting them all together in order to calibrate an HR diagram for all stars. What's really fascinating is that this is a B magnitude and a V magnitude, and these are just brightnesses of stars. And once you have parallax, you can then get distances to almost anywhere by simply getting the brightness of stars in two filters, which you can buy online at Amazon and stick on the back of a telescope and go take pictures with. Doing the parallaxes is hard, but getting an HR diagram, or at least a color magnitude diagram, is not hard. That is something that is within the reach of amateur observers and college students, basically, or even dedicated crazy guys and gals who want to go out and buy a scope and actually try it. There's nothing stopping you except, well, money and time. Other than that, there's nothing really that's stopping you. It's doable and available for people to do. And you can do that because the Hyades and the Pleiades are both things in the sky that are easily visible. So a good amateur project over a summer or a late summer would be to do this. So we just take the Hyades and imagine that it is farther away and those two HR diagrams overlap. And when they overlap perfectly, that's how you know the distance to them. And we just use that distance modulus equation to show how far away they are. And once you have, therefore, the distance to the Hyades, and then you find them, and you can do a color magnitude diagram for any other star cluster, you then calibrate those things together. It assumes that the Hyades are a normal sample of stars. But the good thing is that they have a very long main sequence, and many other star clusters do too. And so the Hyades, being a little older star cluster, still has a good main sequence to actually match up with other clusters. And this is where we're going to go with this. In the very, very, very big thing, we're calling this the cosmic distance ladder. We're going to get out there very soon. And so here we see a good 8 things to kind of get us out to the distances. Across the bottom are 10 times distance each way. Parallax is our first thing that we use in order to get distances to stars. And then we can actually use proper motions and the groups of proper motions to actually show us how far something is. Because if it's running fast, it must be near. And if it's running slow, it must be far. But you have to have large statistical studies in order to do that. But our next set up there is main sequence fitting, or is the spectroscopic parallax solution for distances. And we see that the distance to the Hyades is critical for measuring all those other great distances that are way out there. And we're going to see in order to actually get the distance to the Large Magellanic Cloud, LMC, or M31, the Andromeda Galaxy, or the Virgo cluster of galaxies, or the Coma cluster of galaxies, we really need to get the distance to the Hyades extraordinarily accurately in order to finally get way up in the upper right the redshift. And redshift is eventually what we use in order to show the expansion of the universe in the Big Bang. So it's really funny that we start off with getting parallaxes to nearby stars, and this stepwise function of one thing after another eventually gets you to distances of the entire universe. All right. So what's really nice is that what do we mean by clusters of stars? And so the European Space Agency put together this really nice little video with the Gaia mission that shows us what we mean by a star cluster. And so we have our solar system, and I put the link down there so you can go get to it. And so the solar system, we zoom out and go farther and farther out and farther away. The sun becomes just one star of many, and we can see that we're going to aim at the Hyades, and the Pleiades is just in the upper right there. You can see it as we zoom around. And now we go and orbit the Hyades cluster, the nearest star cluster to us. And we can see that this is what we mean by a star cluster. You see all those bright dots with some glow around them? Those are the stars of the cluster. But we know there's many more stars that are much dimmer, but we're really kind of focused on the bright stars. And there's the Milky Way in the background. And with the Milky Way in the background, eventually we will use this star cluster to help us understand the distances to other star clusters and calibrate the HR diagram so we can get distances to this myriad number of stars that are existing in our Milky Way galaxy, which now we're zooming out of. And the Milky Way galaxy is composed of 200 billion plus stars, and it's about 100,000 light years across. And we're about two-thirds the way out from the center. There are numerous other objects out there in the cosmos, and our Milky Way is just one galaxy of millions. So I invite you to go take a look at the Gaia website, go take a look at these things, go take a look at all of that stuff. It's an amazing, amazing set of materials. So here's some review questions for you to kind of go over to see if you have it. And this is really what we're talking about today is distances. And distances to stars are really critical because they give us distances to galaxies, the size of our Milky Way, the size, and eventually the size of the universe. So spectroscopic parallax is the first step in that great, great, great quest.